Hey there. So the topic of this mini lecture is algebraic data types and pattern matching. And what we're going to look at is the way that you can essentially build, like your own list type in Scala. So let's go ahead and dig in here. So the idea of an algebraic data type is pretty old, and as the name implies, they sort of come from algebra. And if you think about the way we deal with sets in algebra, we have products of sets, which in a programming language these are represented as tuples. And we also have the sum, or the disjoint union of sets. So this is maybe something that's not quite as familiar to you, so I will go through that here. Then what we talk about as an algebraic data type in a programming language, it's essentially the sum of products. So it means that we have different choices, and each choice gives us a list of things. Okay? All right. So I know that's very abstract. It'll make sense in a sec, I hope. All right. We've already seen two examples of an algebraic data type. Those are the option and the list type. And in both cases, we have a element representing the empty option or list. That's none for option and nil for lists. And we have also something that's occupied or non-empty. So that's sum for lists, and it's the cons cell for lists, and sum for an option type. Okay. So we've got two different things. That's the sum, and one of those is a product. In particular, cons cell has two elements. Okay, so I'll show you the syntax. All right, and what's nice about these things is that the way we build them is using these constructors, and we can sort of tear them down or analyze them or write functions over them in exactly the same way that we build them up. So you guys have been doing this already quite a lot, writing lists, functions over lists. And the way you write a function over a list is you almost always do a match with two cases, okay? And that case analysis is looking at the discriminated union or the sum. Oh, that was interesting. There we go. Okay. Algebraic data types happen in lots and lots of languages. This is just a short list. You'll see it's in dozens of languages now, and including some languages which are becoming more prominent. So Swift and Kotlin that I mentioned earlier are two popular languages. I should say that Swift is the preferred language for writing iOS applications, and Kotlin very recently was adopted by Google as one of the preferred languages for writing Android applications, and that's why those two languages are of particular significance. Okay, so there are algebraic data types in lots of languages, and why? It's because they're very convenient to program with. So let's look at the notion of a Cartesian product. This is something that's familiar, I hope. So normally in math, we write this as x times y. So, and that's the set of pairs x, y, where x is drawn from x and y is drawn from y. In Scala, the way we write this is what's called a case class. So when you write class, this declaration, of course, we know that this gives you a little bit of stuff. So when I write a parameterized class like this, I get the class C, and we know I can create a new instance of that class with like 44 and 55 or something. Okay. Oh, sorry, I need a string. And there you go. But note that it doesn't print nicely. I can't do pattern matching on this thing. It's I've got to write all my own support. So what's interesting is simply by putting the word case on the front of this guy, it's still just defining a class, and I think I still can use new on it. But I don't think I need to. Yeah, I can. I think I can also just do that. Yeah. So it works both ways. So what's happened here? Well, I've got the constructor still, and that's still public, but I've also got a companion object that's automatically created for me, and the companion object has an apply method which I can use in the constructor. And note that it's also given me a toString method. So I have a toString method that is doing the right thing. So essentially, what you can see is that when I put the word case in front of it, it means that Scala can go ahead and automatically generate a bunch of stuff for me. Yeah, we don't need to call new. And even more significantly, we can extract elements using pattern matching. All right, so when we've got an instance of C here, we can match on it and sort of get those results out. So here's a function which returns the first element of C. Let me put this in a file, sorry. Let me put it in a file. All right, so we'll put this case class in here. And oh, I know why I got the error. Sorry, I got the error because I didn't put this line in there. Sorry, I need to actually create the instance. There we go. Okay. So anyway, when I put these 3 lines in here now, I didn't name the instance before. It wasn't called C. It was called res59. That's what the problem was the match. Okay. So note that the error messages aren't always the best. The nice message it could have given me was that I don't know what C is. But anyway, okay. So let's try and paste this file in. And you can see it actually comes in just fine. And in fact, it's doing what I expect. In is going to be 5 here. Okay, so what have I done? Rather than calling, of course, I could do this equally, you know, by calling this C dot X. Okay. So note that one thing about case classes is that the parameters are going to be public by default. So they're treated. So all sorts of things change by putting case on here. And in particular, the parameters to the class now are going to be publicly. They will be immutable, so you can't assign to those or anything. But they are public. So by adding case, I get a whole bunch of new capabilities. So I mean, of course, I can use the .x and .y notation still to access the elements of the class. But the thing that I get extra here is the pattern matching. So just to point out that this is not valid if I leave case off. So we can try and load this in. And indeed, I get a problem. I get a problem here when I try to deal with lines. You know, this. I don't know why it's not giving me any meaningful. I don't know what that means. Line 15. There is no line 15. There's only 5 lines for out 6. Anyway, so the error messages aren't very helpful, but it does tell you that the case on here is significant because when I have that there, I can actually do all that stuff. Okay, so it's all just hunky dory. All right. So. We get all sorts of stuff for free by putting the word case onto our class. And what the compiler does is, you know, these constructor arguments are always going to be visible. They're always going to be immutable. So you'll never be able to change them. You can't make these vars. That's not allowed. And you don't have to put val because it's always sort of there. Okay. We get a nice toString method, and we get the companion object, which does sort of some nice things for us as well, including its apply method. And the most significant thing is we get support for pattern matching. The way pattern matching is implemented is very interesting. It's sort of beyond the scope of this course in terms of the detail you need. There's a whole chapter on it in the Scala textbook. So the way it works is that the object has certain methods that are used by the match construct. So as long as an object supports those methods, it can be used in a match, or I should say case. As long as a class supports the unapply method and other things, these extractors, okay, that class then can be matched in a case. So this may look like something really familiar, because you're like, oh, Cartesian products, isn't that what pairs were? So what's the difference? Well, the only difference between a Cartesian product, a pair, and a case class like this is that the case class has a name. That's really all. And also we get to name the fields. Whereas in a product class, they're always called _1 and _2. Whereas here we can pick our own names. But as it turns out, tuples are just case classes. So Scala actually doesn't have a built-in notion of tuple. It's not built into the language. It's just part of the libraries. So Scala has a bunch of these tuples. They're called tuple 3, tuple 4, tuple 5, tuple 6. I don't know how much they go up to, but some number. They probably don't go up to like 25. So whatever it is. And you can see the code. This is actually the entire source code for this class. It's a case class with 3 type parameters, _1, _2, and _3 are of the 3 types. And it's a kind of product. So, and it has this particular specialization of the two-string method. For now, please ignore the plus signs here. These are variance annotations that we will discuss after the midterm. They have to do with how these tuples behave with respect to subtyping. So we'll talk about that after the midterm. But what we can do is, we can look at this and see some of this stuff by invoking the Java getClass method. So Java has a getClass method which we can invoke on any object. And this will tell us what the actual class is. Right? So, if you have a list and get the class, it'll tell you it's there. This is what it actually is. It's a Java collection immutable : : So that's the con cell. Okay. Whereas if you ask about the list nil, that's immutable nil. Okay. So, and you can see here that the triple is actually an instance of tuple 3. All right, so that is the notion of doing Cartesian product. The other thing that we can do, and it's very common, is a union. You guys are used to the concept of union, I hope, from mathematics, and like if I have a set 1, 2, 3, and I have a set 1, 2, 4, if I union them together, I get the set 1, 2, 3, 4. That's not the kind of union we're going to talk about. We're going to talk about something called the coproduct or the disjoint union. And what that means is that if I have the set 1, 2, 3 and the set 1, 2, 4, well, I'm going to get the set of 1, 2, 3 and 1, 2, 4, because the 2 1s and 2 2s are kind of different. They come from different places. This is called a disjoint union, and it's often implemented sort of in set theory by thinking of the elements of the union as little pairs, where the first thing in the pair identifies which side you came from. Are you from the left or are you from the right? So that's called the tag. And you can see the tag is either going to be 0 or 1 in this case, indicating from the left or the right. And then we actually have the value. So we know not only what the value is, but which side of the union it came from. There's lots of different notations for this in mathematics. The circle plus is often used. Also this union with a plus sign in it or a dot. Okay, so the elements then are tagged. In Scala, the way we represent these is using case classes, and we use them as case classes that extend a trait. So a trait is an abstract type in Scala. It's one way of thinking about it. Traits more or less correspond to interfaces. I think that's the best way to think about them in Java. So here I have a trait, date specifier, and here we have two possible implementations or specializations of that trait, which are a date specifier may be absolute, so I want to specify date, and so what I do is I give you the year, month, and day. Or I may have a relative date specifier, which I just give you as an offset with respect to today. Okay, so this is relative to, say, today. And these are two possible ways of creating these things. So what this does is it creates, you can think of this as creating the set of date specifiers where there's two possible disjoint sides, either absolute or relative, and absolutes carry with them a triple, and relatives carry with them a single value. How do I create a date specifier? Well, here let me just give myself an array of date specifiers. So I'll set the first date specifier to be an absolute date, and the second date specifier to be a relative date. So here I'm introducing Scala array notation. It's not that surprising. There are arrays. This is the type of the array, and this is the number of elements in the array. So what I can then do is take a date specifier and sort of resolve it. So how do I resolve a date specifier? Well, the way I'm going to do it is by matching on that date specifier to determine which of the two kinds it is. Is it absolute or is it relative? All right, so this is actually some useful code. What it's going to do is take a date specifier and return a Java calendar object. So Java's calendar object tells me, it's a way of representing a time in Java. Terrible name, but anyway, that's what it is. Okay, so what I want to do is take the date specifier and get the actual, an object representing that time. Okay, so how do we do it? Well, this is some Java business. I'm going to get a calendar builder, and the way we take that thing and then set the date that we want and then build the date. Okay, so this is one way of getting a date in Java. So this is actually the Java APIs. This has nothing to do with Scala. It's Java's calendar and date APIs. So they're not the most beautiful thing in the world, but we can use them here. In any case, so back to the code here. We take our date specifier and we match on it. Either it's going to match absolute, in which case we have a year, month, and date, and we can build the appropriate object, or it's relative. And if it's relative, well, we need to get the current day. So this is using Java's date object, which will give me the current time. And then we can do the appropriate things, whatever we need to set the object to the appropriate time. Okay, so anyway, this is code which is looking at the two possible cases and generating the two possible results. Make sense? I hope so. It's quite a lovely idea that, I mean, you can think of lots of examples like this, like color descriptors. If you have a monitor, you have a RGB or red, green, blue descriptors, and there's CMYK or the cyan, magenta, yellow, black. Okay, and so there's two different kinds of ways of representing color, and we might want to use them in the same context. So what we can say is a color is either a CMYK or an RBG. CMYKs have 4 fields, RBGs have 3, and then you can use them to do various things. Right? So this kind of idea of a disjoint union of products is very, very powerful and useful. So since it's powerful and useful, it must have been around for a long time, and indeed it has. And this is one of the things that different languages do, sometimes radically differently. I just want to show you an example of a horrible design. So I love C. I have to say C is a beautiful language, beautiful in its simplicity. It has a couple of places that are just hideous. I think the type syntax of C is hideous. I think the way it does union types is truly an abomination. So I just want to show you the other extreme of design. I think the design in Scala is quite elegant. It's very simple. It's very easy to understand. It meshes nicely with the object-oriented features. It's great. So what does it look like in C? Okay, in C we have structures. I'll just do this real fast. I'm not going to examine you on this. I just want you to see what it looks like. So here's a structure for absolute dates. Here's a structure for relative dates. That's not so bad, right? So that corresponds to our absolute times and our relative times. And then we get a union, right? So we have a union of those two things. So there's the absolute and relative time. So not looking too bad yet. One of the terrible things, though, about C union types is they don't include tags. So you actually have to manually tag them. So this is very sad. So what I need to do is actually create an enumeration to tell me whether to distinguish these two things. These are the tag types. And now I need another structure which has a tag and then the union of the other structures in it. So this now has a tag saying which kind of thing it is, and then it's got the actual contents. So if you look at all that, if it makes you slightly nauseous, that's fine. That's the same code in Scala. It's doing exactly sort of the same thing, or actually even more, but that's how it happens in C. In C, this is creating an instance of one of these things. This is an absolute date being assigned to array element 0, and then a relative date being assigned to array element 1. And the thing that's really sad here is it's possible for the tag and the union selector to be different, in which case the program just is not safe. So this is another case where safety can be an issue in C, is when we get these tag disjoint union pairs that are sort of out of sync with each other. And this is sort of the matching code written out in C. So here, what do? You take one of these structures, you look at its tag, either it's absolute or it's relative. So if it's absolute, you're going to do one thing and access the stuff, or it's relative and you're going to access the stuff. So this is sort of the story in C. It's quite a lot. It's quite heavy, quite unpleasant to use as a programmer, and super error prone. So much cleaner, less error prone, simpler story when you have real support for these algebraic types, right? So the algebraic types we've looked at so far were simple ones. They can also be recursive. This is an academic example, but this is a representation of the natural numbers. So a piano arithmetic is a formalization of the natural numbers where we count 0, and then the successor of any natural number is also a natural number. So we have two different kinds of piano numbers, the 0 and then successor. These correspond, if you like, to link. You can think of these like linked list nodes where there's no data. All right, so this is the way a horse counts. So if you ask a horse, what's 3 plus 5, he's going to say. So tap it out. So what you say is the successor of 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 the successor. I've already lost count of 0. I am not as smart as a horse. So anyway, that's a Peano arithmetic, or in Peano, the Peano numbers, the Peano naturals. Okay, and we can define functions that actually convert Peano numbers to integers and back and forth, and that can be amusing. But anyway, rather than doing that, I'm going to look at an example which you actually care about, which is the list example. Okay, so it's not that different from the Peano numbers. So here, instead of 0, I have nil, and instead of successor, I have cons. I note there was successor here just took the previous Peano number. Cons takes the previous list and also a value, okay, which is the value for this element. So it's not surprising that there's a relationship between the lists and the natural numbers, because after all, what are the possible lengths of lists? Well, they're from 0 up. We can't have a list of length -1. So they sort of make sense to be like natural numbers. All right? Okay, so this is the list class here. So we're defining the trait at the top level. Then we have 2 instantiations of that, nil and cons. There's a lot of funny stuff here that I want you to sort of blur your eyes and not worry about now. So in particular, there's a plus here and here that we will talk about when we talk about subtyping. And in addition, the type of nil is kind of funny. Nil is a list of nothing. So why does that work? We will discuss that later. It's a similar type to what none has. So none is an option of nothing. So it's an option carrying nothing. So nil is a list carrying nothing. And the nice thing is that if you have nothing, a list of nothing can be treated like a list of anything. So if I have a list of nothing, what may be a list of cats, right? Because I have no cats. Having no cats is very similar to like having no dogs. I have no dogs. I have no cats. I have no Peano numbers. I have no nothing. Okay, and that's why it's given this type. Again, we'll revisit the nothing type when we get to subtyping. Nothing is the bottom type. It's a completely uninhabitable type. There's nothing there. But in any case, so we have the definitions here of our list. There's 2 possibilities, either nil or cons. And note that those correspond to exactly what we do in pattern matching, nil or cons. In the same way we did it with the date selector. Right, there were 2 options. We had 2 things. By the way, there's nothing magic about 2. We can have one case, like we do for pairs, or the tuples. There's usually only one case for those. And a trait can also have an arbitrary number of cases. So if you think about representing, say, an XML document as something like this, you may have a different case for each different kind of node of the XML document. Okay, so in any case, here is a function which we define by pattern matching. And now I can take the length of a list here and mess around with it. Note that this is, when I pull this stuff into the definition, I've now hidden Scala's built-in definition of list, and I lose all of the syntactic niceties that I had there. So I just have my list class. I'm going to have to write out these kind of things a little bit more explicitly. Okay, but anyway, we can sort of go through and do that. That's a list class. So let me show you something that you haven't seen before. Binary trees. So here is a binary tree in Scala, and here a leaf is a tree with nothing in it, and a node has a left tree, a center value, and then a right tree. In this case, we have no data at the leaves. The elements are stored at the internal nodes, okay? And the internal nodes then have left and right children. Um, here is a another type for colors. So we could say colors are either red or black. And trees then are either leaves or nodes. And in this case, I'm going to have keys and values on my trees. So I have keys and values. And here I'm going to represent, this is representing a red-black tree. So my nodes now have keys, values, colors, a left tree, and a right tree. And just to show you, this is sort of some of the code that were implemented to implement red-black trees in Scala. This rotates left, a red-black tree. So what I'm going to do is match on the node and give you back a new node. And this is going to do some matches based on the two nodes. So we're looking here and then sort of moving things around to get the new result. All right. Okay, so that's case classes in Scala. You're going to be doing homework about case classes. So let's take a look at the homework real quick. So I want to pull up the assignment here for FP3. I'll go through the solutions for FP2, but I'll do that in a separate video. Let's instead look at FP3, the assignment. All right. So what you're going to be doing in FP3 is a lot of programming still over lists. So you're writing a membership function, a function to tell whether all of the elements of the list are equal one to the other. So here's some examples to elucidate that. You can see here everything in here is 5. These things are not all the same. One way to think about this, well, you can think about it, but there's lots of ways to implement all equal. But you should be able to do this in linear time, not quadratic time. So if you think about it, the empty list is always going to give you true. A singleton list will also always give you true. And now I'm checking whether they're all equal, right? So I can just take the first element and now go through and make sure everything's equal to that for an element of 2 lists or 2 or more. Okay, so there's a way of writing this that's quadratic, which is that you just check for every element that every other element is the same, and that's not the best way to do it. All right. Here's a function string length, which it's going to compute the length of each string in the list and return the original strings paired with their length. Okay, so you start off with the rain, you should return the pair of elements the and rain. And here you're not supposed to use recursion directly. Instead, you're going to use the map method. So note, these comments here are very important. So when you're doing these, you need to follow the rules that are given. So in this case, you need to use the map method. Here, you're supposed to write something recursive. So this is a recursive definition, which is going to delete things from a list. So it says complete the function definition for delete one that takes an element x and a list y's, returns the list where any occurrence of x have been removed. Okay, so in this case, for example, we remove all the occurrences of the in the result. This definition 5 is expected to be written using 4 comprehensions, not using recursion directly. So there you need to go and write the same function using a for loop. Here you need write the same thing using filter and no recursion or for loop. Here I want you to write a remove dupes, which is going to remove duplicate elements that are adjacent to each other. So again, this can be done in linear time. You should not need to go through the list multiple times. So you want to write a definition where you can actually compute this just sort of rolling forwards. And the same thing here, this one is expected to be written recursively. And this is the same, except we're going to count the things that we're removing. So we'll count all the things being removed here. This is the function split at, which I actually showed you earlier. Scala has a built-in version of this that, well, it's actually similar to this. The version I showed you, like, split a list into two separate lists based on a predicate. Here you're going to do it based on a count. So the first in elements go on the left-hand list, and the rest of the list goes on the right. And finally, all distinct here. So is going to tell whether all the elements of a list are distinct. This one is allowed to be quadratic. Okay, so you can write this in a quadratic form. The easiest way to do it is to call your member function, and therefore quadratic time is okay. Okay, actually I misspoke. There's not an exercise here on using case classes. You'll have some problems about case classes in the quiz though for this week, so make sure you look at those and let me know if you have any questions. Okay? All right, thanks a lot, and we'll see you soon.